thank you for coming for the first session of this meeting in memory of me. And our first speaker is Dr. Stuart Antman from University of Maryland, and the title you can see on the screen. And after that we have the coffee break. But now we give the welcome.
Thank you. "37 years ago, I made my first of many visits to UNAM and had the pleasure of making many friends. And one of my chief hosts and one of my very good friends was Minzoni. And then, in all my subsequent visits, we had many freewheeling discussions with him on many aspects of applied mathematics. And here is one photo from my first visit showing us working away in deep concentration. You probably recognize. That's Tim on the right. I miss him very much. So to start with, I want to talk about some problems with symmetries. And the English word for the symmetries are not very effective. We sometimes call things axisymmetric or radially symmetric. And unfortunately, we have to use the group theory terms to be very precise. So a radially symmetric deformation of this ring with rays will go into one where every point moves radially outward. And a rotationally symmetric motion would be one where every point moves both radially outward and moves, in this case, in the same sense about the solution. And we're looking at a number of problems that will have these kinds of symmetries. For the notation is very, very difficult for these. The inner radius is going to be, the inner radius is going to be A, the outer radius is going to be 1, and a typical radius is going to be S. And if we look at a deformation, the point that had a radius A will have the new radius R of AT. This will be R of typical radius R of S of T, and the outer radius R of 1 of T. So first I want to talk about a few very simple problems that have been done by others. And first of all, I'll talk about Dervish motions of a ring. So Dervish motion is constant whirling with the arms often vertical. We'll ignore the arms for a while. And the simplest problem is that you model the configuration of a thin annulus by in this case, a curve, which is a circle, every point of which is equipped with a cross-section, which is going to be a vector, and the vector can rotate and stretch. And in a Dervish motion, we can think of this annulus as both breathing, changing its radius, and rotating simultaneously, just as dervishes do. And this is the case where the annulus has contracted and the cross-sections have sheared in one sense, and here's the case where the annulus has inflated and the cross-sections sheared in the opposite case. And so we can ask the question, is there a shearable, non-linearly elastic or viscoelastic ring that has a simple unforced motion in which it rotates, but the cross-sections stay perpendicular to it? So it rotates and oscillates radially, in which there is no shearing. If you look at the equations that have shearing, it's governed by an 8th order system of nonlinear ordinary differential equations. And if you look at the equations, or if you think, you find no because of conservation of angular momentum. So you can't have cases where the cross-sections stay perpendicular unless you constrain the motions so that the cross-sections cannot rotate relative to these curves. Now, you can make such a constraint by saying that the ring is unshearable. If you have an unshearable ring, there is such a motion. But what happens in those cases is that the shear force along the normal direction itself oscillates. If you look at the general motions of these things, with these kind of breathing and rotating motions, you get a very pretty Hamiltonian structure of nonlinearly elastic rings, and that the Hamiltonian structure supports nice proofs of periodic solutions. And if you're going to look at problems that have periodically forced for viscoelastic rings, you can use that same structure again. That's one problem I'm not going to talk about. Now I want to talk about briefly another problem. You look at an incompressible annulus, and the equations are exactly the same if you have a cylindrical shell. And so we let I, J be fixed orthonormal basis for the plane. Polar coordinates are going to be S and phi, and we take a standard rotating unit basis E1 and E2. And we just look for purely radial motions. So the position at time t is going to be an unknown function r, depending upon s and t, and the unit radial vector. And now we make the requirement that the material be incompressible. So we compute the Jacobian of this transformation in polar coordinates, and the requirement that the Jacobian be equal to 1 gives us this equation. And this equation is a trivial ODE, and that says the radius at any s at any time t is this square root, and it depends entirely upon the radius of the inner boundary. Then we write down the general constitutive equations saying how the stresses depend upon the strains, and because the material is incompressible, there's going to be a Lagrange multiplier. P, which is popularly known as the pressure. If you eliminate that Lagrange multiplier, use boundary conditions, you show that the entire motion is completely determined by an ordinary differential equation for the inner radius. And if you know the motion of the inner radius, you know the motion of any radius. So this beautiful solution was found by J.K. Knowles in 1960. It was the first time anyone had an ability to really solve a dynamical problem of nonlinear solid mechanics for arbitrary materials. And Knowles was at Caltech, and he could possibly have been an instructor of Tim when Tim was a graduate student. For doing this for other materials, there are a number of papers by Carmen Calgary. And you can do exactly the same game for spherical shells. And the last thing in the background is blow-up. And in 1978, John Ball showed that there are initial conditions for which any elastic body that's topologically equivalent to a spherical shell, and if you subject it to a prescribed internal hydrostatic pressure, hydrostatic pressure is force per actual area, then there are materials for which the dynamic solution blows up in finite time. That is, the radius becomes infinite in finite time, provided you choose appropriate initial conditions. So you don't want the initial conditions to try and compress it. The stored energy function shouldn't be too strong. If perfectly reasonable, grows less than cubic in the appropriate strains, and if the pressure is sufficiently large. And we'll look at some additional problems. And this is a result that seemed very, very terrifying when it first came out. If you try blowing something up, it may actually explode on you. The material, of course, would give way. But it's not so bad, because hydrostatic pressure is force per actual area. It's not force per the original area, the reference area. So if you try to raise the pressure inside the body, say by trying to pump more air inside the cavity, then the added air would tend to stretch the boundary. And the pressure is force per unit actual area. So trying to raise the pressure, you're going to be raising the denominator. And so for many materials, trying to raise the pressure, trying to make the pressure a control, is going to be very artificial. Under analogous conditions, and they are likewise artificial, cylindrical shells will blow up in infinite time. I'm going to be talking about some natural controls when we get some more funny things. So now I want to briefly talk about some non-elementary problems. These are going to be governed by partial differential equations. And first of all, we want to look at radially symmetric motions. And these are going to be governed by specializations of the exact three-dimensional equations. So they have certain simplifications. The obvious one is that there's simply going to be one spatial variable. If you have problems with more independent spatial variables, the systems become very difficult and for the most part are completely open. And if you look at quasi-linear hyperbolic systems, which govern elastic motions, the theory for more than one space variable is very complicated and it's completely open. They have a second complication, though whatever you do in one dimension has effects in the opposite direction. It's like squeezing a tube of toothpaste. You're squeezing in a sort of radial direction, but the toothpaste is going to come out in the longitudinal direction. And that's one of the problems that has to be accounted for. Then we're going to look at rotationally symmetric motions. And these are going to be governed by, again, the exact three-dimensional theory. And everything that counts is the constituent equations, how the stress depends upon the strain. And those are wide open. Basically, all sorts of materials, rubber, steel, new materials that people make, biological materials have completely different behavior. And so we're trying to find out what are thresholds between different materials that give qualitatively different behaviors. So I'm going to say a few words on the formulation of the equation. You will not be tested on this stuff. We let P of Z be the position at time t of a material point, and this should be a Z, zeta, in some reference configuration. Then the gradient of position with respect to the original position is F, and the symmetric deformation tensor based upon F is the transpose of F acting on F. This is a positive definite symmetric tensor. F has to have a positive determinant so that the deformation always preserve orientation and you never get a total squashing. And then the force per unit reference area is the Piola-Kirchhoff stress, and so for a viscoelastic material, this force intensity depends upon the deformation and depends upon the rate of deformation. And in order for the material to be real and to have not to depend upon rigid motions, this function must have this very specific form. An elastic material doesn't depend upon F sub t or C sub t. And an elastic material has a strong stored energy if you can find T and write it as a derivative of scalar energy with respect to that tensor. So the equation of motion is the mass density. This is the mass density in the reference configuration. It's fixed. It's given to us. It's not like the density in fluids. acceleration term, a divergence of the stress, and any additional force that you want to throw in there. And the classification of this system as a partial differential equation depends entirely on the constitutive equation. Whether it's going to be elliptic, whether it's going to be parabolic, whether it's going to have any sort of memory. And if you're going to be studying elliptic problems, there is unfortunately a very natural condition, which is fairly hard to interpret, but that says the more you pull something in one direction, the more effect you're going to get, but there are going to be effects in transverse directions that have to be under control. And so the first condition is a strong ellipticity condition. It says that you take the derivative of this tensor with respect to the second tensor, which is the 9 by 9 matrix, and you saturate it by matrices of rank 1. And this is the standard notation for a dyadic product, but I see no need for the funny little cross. Now, a monotonicity condition looks very much the same, except that instead of the tensors or matrices of rank 1, use arbitrary matrices. So this is a much stronger condition, and it would really make the mathematics look very nice. It says that a stored energy function, if you stick the stored energy function in here, so it will be the second derivative of W, that would be convex. I said that's great if you're a mathematician, but you have a convex function on the set where the Jacobian is positive. And if you look where a Jacobian is positive, it's a non-convex set. And for certain deformation, it may have a countable infinity of non-convex components. So you can't have a convex function blowing up on the boundary of a non-convex set. So that's one of the first difficulties with that. And that messed up a lot of mathematicians. It prevents material properties from being invariant under rigid motions, and it ensures that any sort of equilibrium problem has a unique solution, so you can't have any bubbling. If you use a strong ellipticity condition, then you get quasi-linear hyperbolic systems. And this is a wide open subject. So now we'll specialize our attention to annuli and very specific motions where the annulus is subject to a purely radial motion, but when it stretches in a radial direction, it must also stretch in the azimuthal direction, in the circumferential direction. And we'll look only at rotationally symmetric motions. This was basically the issue that we discussed earlier. R of S of t is the radius at initial radius s at time t, and then the stretch in the circumferential or in the azimuthal direction is just the radius divided by the original radius, and the radius in the stretch direction is derivative with the radial position with respect to its original position. And then we have two forces, one force in the radial direction and one force in the circumferential direction. And for nonlinear elastic materials, this force intensity depends upon the two stretches, and so does this. If you want to talk about a viscoelastic material, you have the dependence of these functions on these two stretches and their time derivatives. And now we get something that's rather funny. The strong ellipticity condition says the more you stretch something in the azimuthal direction, the more force you require. You won't object to that. Same thing, what's happening in the radial direction. There's a Poisson ratio effect, which is sort of the same effect that we described for toothpaste tubes. If you pull something in one direction and you don't want any shrinkage in the transverse direction, you better prevent it from doing so, and so you apply the tension. And then we have something that looks like the monotonicity condition, for which we gave a sermon that should not be used. And this says that this matrix of the as a consequence of the monotonicity condition without the quasi in front of it that we gave 4 objections to. And so it would be a nice condition, but we'd want to throw it out. Now, one of the objections was that the equation should be invariant under rigid motions. But if we're looking at this purely radial effect, there's no real rigid motions going on, so we don't have to worry about that. The domain of our constitutive functions, our deformations, is this convex set. And we excluded the monotonicity condition for the 3-dimensional theory because we wanted the function to be able to blow up on the boundary of a non-convex set. We don't have to worry about non-convex sets. This is as convex as you can get. It's quadrant with strange space. And so this has no effect. So this means that this very simple assumption that we were talking about would seem to be disqualified. However, if you look at the consequences of the monotonicity condition for problems like this, there are further consequences that are absolutely make no sense whatsoever. That means, for practical purposes, we can use this condition. It's not incompatible, this condition is not incompatible with the strong monotonicity condition that we gave a sermon against. So that simplifies some of our problems and makes some of the analysis a lot more attractive. Now for the analysis, these are things that require getting a lot of nice a priori estimates, and some of you may know about a priori estimates, some of you don't, but for those of you who know, it is something that's done best in the privacy of your own home. And so we won't do any here, but the basic trick is to start with the Fayedo-Bugno-Yorkin method, and this method makes a representation in a finite series, say a finite Fourier series with explicit space dependence and unknown time-dependent coefficients. These can be orthonormal if you're smart. You stick it into the weak form of the equations, which is nothing more than the physical principle of virtual power. You get a finite system of ordinary differential equations for these things. You start getting your estimates. First estimate is getting an energy estimate. And then you get some more, and you get enough estimates to ultimately show that the series that you get for R sub n, as big M goes to infinity, is going to converge, some of its derivatives are going to converge in an appropriate sense, and then you're going to get yourself a nice limit function, and you show that limit function satisfies the weak equations, and then you go show that the equations have solutions that are a little bit smoother than you want. To get these estimates, you have to use not only the monotonicity condition, but also other conditions that requiring that viscosity becomes infinite at a total compression. To get a total compression, you may very well want to say the force better be infinite. Or I should say prevent a total compression, but you also it seems reasonable to ask that viscosity become infinite at a total compression. If you look at the Navier-Stokes equation for compressible fluids, and you convert that into the Lagrangian formulation, the material formulation, you find that this condition is exactly true for the Navier-Stokes equation for a compressible fluid, but you never see it when you use the Euler-Liouville formulation. So you have all these additional constitutive equations, constitutive restrictions that make all the analysis go through. And since we only have 15 more minutes rather than 15 more days, we will skip it. Now we want to talk about blow-up under centrifugal force. We discussed Ball's blow-up theory, and they had as a control an internal pressure, and as a control, it was not very controllable. And so now we're going to, I don't have actually a picture, you have cylindrical shell, you weld it to a rigid cylinder on the inside, turn the rigid cylinder at angular speed omega, you have a deformable cylindrical shell. What's going to happen to it? The equation of motion, the density which is given to us, you have two time derivatives, you have a gradient of the stresses, and you have the centrifugal force, which can also be called the centripetal force. If you read any of the old books on mechanics, they had long debates what it should be. Well, it depends who it's working on. For working on one body, it's the centrifugal force, and the other body is centripetal force, because they're equal and opposite. So those discussions are nice if you don't have to bother understanding them. Again, we have the inner radius A is fixed, the outer radius is traction-free, no force on it. This is the boundary condition, which is trivial. The rotation is taken because we're using a rotating coordinate system. What's the first thing you do? You get an energy estimate. So you multiply the equation of motion by r sub t, integrate everything by parts over space-time, use the boundary condition, and you get the energy equation. You have a kinetic energy, a stored energy, and we have the kinetic energy of rotation, and that is going to be a constant there. We have no dissipative mechanisms, but the same game we go through for dissipative mechanisms. Kinetic energy is 1/2 the mass times the velocity squared. The stored energy is just the integral of the point-wise stored energy. And now we define an amplitude function, capital psi, and this is just the stretching squared with the weight function, the density. And then simply take its time derivative. That's not too difficult. Take the second time derivative. And when you get the second time derivative, you get an r sub dt. Then you go back to the equation of motion, which I won't go back to show you. It happens r sub tt equals something. So we replace this r sub tt by the expression on the preceding page. And you can believe me, and then you get the second time derivative can be expressed in terms of kinetic energy, stored energy, this constant of this energy constant, then an effect due to the rotation, and this quantity here, which depends very closely on the constitutive equations. And now first of all, because I'm going fast, and secondly, because I would never remember that equation from one page to the other, there's the same equation. This stuff all makes sense. This stuff looks a little bit weird. It says something about the constitutive equations, and I'm going to assume that the material is weak. But before saying why I assume it's weak, what I really want to do is control this integrand. And so I say I'm going to control this integrand with the equation which I call the deus ex machina, and say that the total energy is going to be controlled by the stuff that depends upon this integrand. And the only way that this differs from the integrand is the power of s. And now we're going to throw on another expression, which is an arbitrary constant depending upon the angular speed omega squared. And then if we throw in the fact that n is the derivative of energy, we get this expression. And so we have an inequality, W being greater than this thing, which again is still deus ex machina, because it looks like it was pulled out of the air. And I'll give the explanation below. But if we do that, we are able to throw away all this stuff, and right side Tt is greater than 4 times the kinetic energy minus the energy constant. And now we're going to assume that minus 2e is greater than 0, and that means that the initial state is sufficiently inflational and the angular velocity is sufficiently large. And then you go from this equation to this one. And now we go look at psi sub t, which is going to be lurking around here. We use the Cauchy-Bunyakovsky-Schwarz inequality. And we have our psi sub t, which was on the preceding page. Well, that was just the derivative of r minus r sub t squared. So you get the r sub t out here. You use the Cauchy-Bunyakovsky-Schwarz inequality, break it up into the square root of two integrals. We observe that this quantity is just the square root of 2 times psi. This is just the kinetic energy. And so this quantity squared is less than 4 times psi times k. And you simply rewrite it as 4k is greater than psi inverse psi sub t. And we rewrite that equation up here, and then we rewrite it yet again in this form. And so you have the derivative of one logarithm is less than the derivative of the other. Quotation marks means that you just be careful about dividing by 0. And you solve that, that says that psi grows exponentially fast, provided the original derivative of psi is positive, so things are starting out to inflate. So now we have to ask, what is the significance of the deus ex machina? Here I've rewritten it in terms of W. We're simply going to make an additional minor assumption that W grows faster than tau, that the energy grows faster than linear. Well, most energies you expect to be at least quadratic. And we take this equation, we introduce polar coordinates for it. Xi is going to be, well, excuse me, new variables. Xi is this quantity, capital Y is this, with the inverse tau, and subject this to the deus ex machina, which becomes another equation for Y. As soon as you see the form on the right-hand side, that tells us, let's do polar coordinates. Right here, rho and theta. This is the antique form of rho, the antique form of theta. And then that gives you, that converts this inequality to 1. That is nothing more than a linear differential inequality. We can solve that, telling us what W is, which is just Y, and it has to be less than a quadratic function. So it has to be weaker than a quadratic function, but it can be raised to this speed. That says that the bigger the speed, the larger the angular, the bigger the angular speed, the stronger the material can be that can allow blow-up. So here we get a very rich answer of the blow-up problem. Briefly here, since I see that time is moving, I want to look at Knoll's problem for rotationally symmetric bodies, and I'll zoom through that rather fast. We found out that if you look at purely radial motion, and Knoll's problem reduced everything to ordinary differential equations. Now we have a much richer problem, incompressible medium, and can we still get an ordinary differential equation? We'd expect no, we'd expect the system to be governed by a quasi-linear hyperbolic or parabolic hyperbolic system. So I will zip through that expression. Introduce polar coordinates. Introduce a rotationally symmetric motion. That's where every radial fiber can stretch in the radial direction and rotate at the same amount. This is what the deformation would look like. Psi says how much an angular rotation. You compute the deformation tensor, demand that it be characterized incompressibility, so it equals 1. We get an exact same sort of equation that the radial position depends solely upon the radial position of the inner radius. So R depends upon a single function of time. What about the rotation psi? Well, if we go to the equation for an incompressible elastic body, there is a Lagrange multiplier corresponding to the incompressibility condition, which we write in this form. Here's the equation again. Now, this is a certain vector in tensor space or matrix space. So any part of SA in that direction can be absorbed by this, as long as we change lambda. We'll make a very, very special choice of SA. That will give us a very special choice of lambda. If we make this choice, demanding that it be orthogonal in the tensor sense to C, then this lambda becomes P, the usual pressure, the usual force per unit actual area. You go look at this equation, it has no T derivatives. So it's sort of an ordinary differential equation for psi in its dependence upon S. Solve that ordinary differential equation, everything in sight depends upon T. That means any one of these motions can be governed by ordinary differential equations. Now I'm talking about special motions, and in these motions we expect that the dancers not only have bodies that inflate when they spin, but they also have arms. So here is a mathematical arm. This arm has a rigid body at the end. This is a deformable arm. This is a problem a little more interesting. This is a rigid cylinder. Inside the rigid annulus, inside the rigid annulus is a spinning rigid cylinder, and that exerts a stick-slip friction on the outer cylinder. The stick-slip friction we know in Froude's problem for a pendulum, the ordinary differential equation, has a beautiful attractor. Does this system have an attractor? The interesting thing that I did want to point out, though, is that if you want this body at the end to be big compared to this deformable body here, you have two small parameters. Namely, the ratio of the mass of this small body to the mass of the big rigid body, and the inertias of the small body with respect to big bodies. So it's an asymptotic problem with two small parameters. Well, if you go to the traditional asymptotics theory, everything's fine, you have two parameters, but you always make one dependent upon the other. And there was once a book written by O'Malley where he really looked at two-parameter problems, but it was never published. So here we have a two-parameter problem, asymptotics, but there's a way to get our hands on it, because we can look for attractors of these equations. A nice book on attractors is one by Antman, showing that certain partial differential equations really have a small finite dimensional attractor. Well, here you can estimate the dimension of the attractors in terms of the small parameters. And so when this is heavy with respect to that, you can basically characterize the motion by a fairly small collection of partial differential equations, and you can make them smaller by just making this thing bigger. So that's another way to get one's hands on asymptotics of nice physical problems. This is a three-dimensional picture of that, and so I thank you for your attention.
if I remember these estimates of Timan about the attractor, I remember you said they are small dimension, but how small it is, because if I remember some of his estimates, so some of the estimates of the number of dimensions of the attractors are really huge. Like 100.
That's right. He was studying the Navier-Stokes equation.
Yes.
But here we have two small parameters that can mess up the equation. If I wrote this thing down in all its full glory, this particular problem has only one space dimension, but if I write it down in all its full glory and then found the dimension, it would be gigantic. But again, we're controlling them by smashing a couple of parameters in the equation, making them tiny.
But the attractor, do you have an idea of, in reality, how many dimensions does it have?
You can estimate the dimensions very nicely and say that if certain pieces of data satisfy certain inequalities, you can estimate it. And in fact, for some of these problems, you can show the dimension can be made down to 1 or 2.
Okay.
So, for example, suppose you have a mass on a spring. A spring is a 3-dimensional continuum. You would like the mass on a spring to be governed by what we teach to elementary students in physics, that is governed by an ordinary differential equation. You can get your hands on that for a problem like this. And presumably you get your hands on some fluid dynamical problems if you really did some serious games with the parameters.
Thank you.
In these law of problems, is there also a law of infinite time, or this is an infinite time?
These particular problems require infinite time, and it gives exponential blow-up. And the only case where you have that is in the inflation of a 3-dimensional body under elasticity or some viscoelasticity, where you have dissipative mechanism. But again, there you have a very strange control, and if you analyze the control, it's funny. None of this happens for 2-dimensional problems or any of the subsequent problems that I spoke about.
In these problems, is it also that below a certain energy, for example, you assume something on the energy to get this started, but below some energy, can you say that solutions are always nice or
I would say yes. That is, that you can control the energy and do the regularity theory. And so there's sufficient conditions ensuring blow up, and for many of these you can control the energy. What you have to do in that case is get the refined a priori estimates to justify the global existence theory by using the Fayet-Bourneau-Yorkin method.
Another question. I have a final question. The definition of the amplitude equation, you get this inequality of the second derivative. The amplitude equation looks like the same definition of the inertial moments of the rigid body, isn't it?
Yes. All these problems for deformable bodies have inertias just that are much richer than what we all know for rigid body mechanics. Of course, rigid body mechanics is just a special case of this. But there was over here, there was a special choice. So that's a reasonable way to think of it as a moment of inertia, about that. And it's crucial that you have this minus sign, because otherwise all the algebra gets very messy.
I remember in celestial mechanics when you see the many body problems, there are similar inequality of the second derivative of the inertial moment. Have you seen this relation between this problem of many body problems and this problem of the elastic?
I have seen it, but I haven't thought about it until you raised the issue.
Just one last little question, or not even a question, from a very naive perspective. I can't follow most of this, but I'm trying to think of what kind of concrete actual system would fall under this theory. And I was sort of thinking, what can you say about, is any of this relevant to, say, a potter spinning his pot on a wheel, or a glass blower who is...
I would say maybe appropriate to centrifuges when they are spinning things very, very...
Like the ones in Tehran?
Not an expert on that.
So they've actually ran centrifuges and observed failures, and failures are related to this theory?
No, what I would like to point out as, I would say, the moral of this, these are just specific, you can almost think of these as academic problems, but what they show, one moral, is that if you do not make any assumptions a priori about the strength of the material or about the constitutive equation, there are many problems that you can solve, and in those problems you will find thresholds distinguishing materials that have qualitatively different behavior. And one of the dangerous parts of those thresholds is that the thresholds often talk about material that has quadratic growth in the energy. Linear theories have quadratic growth. And so anyone doing, let's say, numerical computations for linear theory has a 50% chance of being on the wrong side, finding that the system would be safe, whereas in fact it could be dangerous.
Thank you.
Question?
Maybe this is absurd, but in some of these extreme cases, like in the total compression you were talking about, depending on the height of the dynamics of how you do this, you do not get shock waves. Can you solve these kind of things in reality?
Okay, so I'm talking about total compression because I wanted constitutive equations that would prevent it.
Oh, okay.
Any one of these problems for elasticity could very well give rise to shocks. And basically, the situation for shocks, hyperbolic conservation laws, is that it's pretty good if you have one independent spatial variable and one second order equation. And if you make nice assumptions, like the lax, Oleinic, lax, and mu assumptions, but some of these materials don't satisfy that. So there are many beautiful, complicated, open problems associated with elastic behavior and shocks. And some of them look like they're even simple.
We say thank you again.
Thank you very much.